In this topic, we will examine the controls and indicators of the secondary flight controls. The secondary flight controls on the Fokker 100 consist of the flaps, speed brake, and lift dampers. In addition, we will discuss the operation of the stall prevention system. We will also examine the takeoff configuration warnings generated if the aircraft flight controls are not configured for takeoff. The secondary flight controls consist of the flaps, the speed brake, and the lift dampers. As you may recall from an earlier module, all secondary flight controls are powered by hydraulic system 1. The inboard trailing edge of each wing incorporates two sets of flaps, known as the inner flaps and the outer flaps. The flaps are mechanically driven from a main gearbox through drive shafts and mechanical actuators. The main gearbox is hydraulically driven in normal operations and electrically in the alternate mode. Each flap section has a mechanically operated leading edge vane. The response time for the flaps to reach full extension is 20 seconds under hydraulic operation and 90 seconds in the alternate electrical mode. The flap selector is located at the pedestal and allows the flaps to move between a range of 0 and 42 degrees. Gates are situated at 8 degrees and 25 degrees selecting down, and at 15 degrees selecting up. Flap position is shown on a flap position indicator located at the main instrument panel.
Flap position indication is also displayed on the PFD.
The flap selector operates the flap control valve, which allows the flap drive to operate. This enables the flaps to move to the selected position. Feedback is sent from the flap drive to the flap control valve, causing it to shut off when the flaps have reached the designated position. The flap position computer also receives data from the flap drive as well as receiving flap selector information. Disagreement between the flaps and the flap selector after flap travel generates an alert. Flap asymmetry is conveyed to the flap position computer.
The flap position computer relays flap position data to the flight warning computer, GPWS, stall warning computer, and to AFCAS.
In addition, the flap position computer controls the shut-off valve, removing hydraulic pressure to the flap control valve. The speed brake forms the tail section of the aircraft. During normal operations, the speed brake is hydraulically powered by System 1. The speed brake is controlled by a speed brake lever located at the pedestal. The speed brake consists of two conical surfaces that open to increase drag. The speed brakes can be deployed at any speed. Above 190 knots, the speed brakes open until there is a balance between the hydraulic forces in the actuator and the air load on the surfaces. Below 190 knots, the speed brakes open to their maximum 60 degrees. The speed brake is operated by the speed brake lever located at the pedestal. Selecting out will extend the speed brakes.
The speed brake extension is inhibited after toga trigger or with the thrust lever above minimum takeoff position if the landing gear is up. The speed brakes will retract automatically if the toga triggers are pulled or if the thrust levers are above minimum takeoff, provided the landing gear is up.
The lever will return to the in position during automatic retraction. The speed brake can be manually retracted by pushing the lever forward to in. When the speed brakes are extended beyond 5 degrees, the blue speed brake lights illuminate at the main instrument panel. The lift dampers are powered by hydraulic system 1. The lift damper system consists of 5 doors on each wing that are either fully in or fully out. all lift dampers operate simultaneously. When the lift dampers are in, they are locked flush with the upper wing surface. The function of the lift dampers is to destroy lift and achieve more effective braking after touchdown. The lift damper surfaces are extended and retracted by hydraulic actuators. In the event of a hydraulic system failure, accumulators provide an emergency source of power sufficient for one extension and retraction. The lift dampers can only be used when the aircraft is on the ground after touchdown, during the landing roll, or during a rejected takeoff. A blue memo message is displayed at the MFDU when the lift dampers are extended. Hydraulic fluid in System 1 that powers the lift damper actuators passes through a safety shut-off valve and a control valve. The lift dampers can be prepared for automatic extension by means of an arming system. The automatic extension system can be armed in the air for landing and on the ground in case of a rejected takeoff. The arming system is activated by pressing the arming push button at the pedestal. A blue arm annunciation indicates the system is armed. If armed before takeoff, the system is automatically disarmed at liftoff. If the system does not disarm, an alert will be generated.
With the system armed during a rejected takeoff, the lift dampers will extend when the thrust levers are retarded and the speed is above 50 knots. When armed before landing, the lift dampers extend when the wheels spin up and both thrust levers are in idle.
The lift dampers will retract automatically in a go-around if the lift dampers are armed and either toga trigger is activated or the thrust levers are advanced to maximum. The lift dampers will retract when the thrust levers are advanced or the system is disarmed. The system is disarmed by pressing the arming push button again, causing the light to go out. In manual operation, the system is not armed. The lift dampers will extend on the ground once reverse thrust is selected. The lift dampers retract when the reverse thrust levers are reset. Faults will be enunciated by the lift damper system push button located at the hydraulics panel. The push button is guarded. Pressing the push button inhibits automatic and manual extension of the lift dampers. Pressing the lift damper system push button will also close the shut-off valve and control valve to prevent lift damper extension should the system become unsafe. We will discuss this push button in greater detail later in this module. We will now examine the stall prevention system. This system provides for pre-stall warning and post-stall recovery. The system consists of two angle of attack vanes located towards the nose of the aircraft.
Data is sent from the flap position computer and the angle of attack vane to the dual-channel stall prevention computer. In addition, a stall prevention enhancement unit is installed. The SPEU inhibits stick pusher operation during wind shear and to synchronize stick shaker activation at high altitude with AFCAS.
Two stick shakers are located behind each control column. The pre-stall warning will cause the stick shakers to shake the control columns. Each computer is able to activate both stick shakers. The stick shaker system is armed during the takeoff roll and remains armed in flight. Ground proximity warnings are inhibited during stick shaker operation. Post-stall recovery is provided by a stick pusher that pushes the control column fully forward for maximum aircraft nose down. Both stall computers must detect the stall condition for the stick pusher to operate. The stick pusher is inhibited until 45 seconds after takeoff. A stick pusher disconnect handle is located at the pedestal. We will discuss this later in the module. Finally, in this section, we will examine the takeoff configuration warning system. Distinctive Level 3 takeoff configuration alerts will be presented if either thrust lever is advanced to the minimum takeoff position when the aircraft is on the ground and is not configured for takeoff. The alerts cannot be cancelled by pressing the master warning lights. Takeoff configuration alerts are presented if flaps are not in the takeoff position or the flaps are in alternate operation mode. The stabilizer is not in the takeoff position, the parking brake is not released, and the speed brake is out. Also presented are alerts for unlocked lift dumper doors, the flight controls are not unlocked, and one elevator hydraulic system depressurized. This condition will also present a local elevator fault light at the hydraulics panel. The takeoff configuration can be tested prior to takeoff with the parking brakes set by pressing the takeoff configuration push button located at the pedestal. We will discuss this in the next section. Finally, the takeoff configuration alerts are inhibited as shown. In this section, we will examine the operation of the secondary flight controls.
The flaps are operated by selecting the flap lever to the required position. The position is indicated by the flap position indicator and the PFD.
Touch the flap lever to lower the flaps. Alerts for flap disagreement and asymmetry are presented in the usual manner during normal operation, and these will be discussed in the next section. Manual operation of the speed brake is by the speed brake lever, also located at the pedestal. Touch the speed brake lever to extend the speed brake. The speed brake is now extended as indicated by the blue speed brake lights. The speed brake can be retracted automatically or manually. If automatically controlled, the lever will still return to the in position.
The lift dampers will extend automatically when the system is armed. Extension takes place when the wheel speed is above 50 knots. Manual lift damper extension is accomplished by raising both thrust levers if the aircraft is on the ground.
Automatic operation is achieved by pressing the arming push button. Press the arming push button to arm the lift dampers. With the system armed, the lift dampers will extend automatically during a rejected takeoff. The system is automatically disarmed at liftoff and will require rearming before landing. We will discuss system faults in the next section. Operation of the stall prevention system is fully automatic. Faults will be discussed in the next section. Concluding this section, we will examine the operation of the takeoff configuration test button located at the pedestal. Depressing the push button tests the aircraft takeoff configuration prior to takeoff. The parking brake can remain set. Test the takeoff configuration now. Finally, if ready for takeoff, a blue memo message saying Takeoff Configuration Normal is presented at the MFDU. The parking brake alert will be inhibited.
A flap position computer fault generates a Level 1 alert and is given in the QRH. The autopilot should be turned off, then on, to try to rectify the fault. This has cured the fault on the right PFD, but not the left PFD. The AT1 is now turned off, and an alternate FCC is selected. The GPWS flap override switch is now selected to on. A flap position computer fault is inhibited as shown in the diagram.
Alternate operation of the flaps is achieved by using the alternate flap switch located next to the flap lever. The alternate system is electrically operated and deactivates the hydraulic system.
In addition, the alert for flap disagreement is inhibited and flap asymmetry protection is not provided. During alternate operation, however, the associated alerts still occur with alternate flap operation.
Alternate operation of the flaps will be required if hydraulic system 1 has to be switched off. The alternate flap control is operated by lifting the switch to unlock it from the center position. Pushing the switch aft will extend the flaps. Pushing the switch forward will cause the flaps to retract. The switch is spring-loaded to the center when released. Flap asymmetry will produce a level 2 alert, and the relevant alert and procedure to be presented at the MFDU. Flap asymmetry procedure is given in the Quick Reference Handbook. Flap asymmetry will deactivate the normal hydraulic flap system, and the flaps will remain in the position at which the asymmetry occurred.
Using the alternate flap system may amplify the asymmetry.
Use the landing procedure for flaps less than 25 degrees if required. The flap asymmetry alert is inhibited by the FWS during flight phases shown in this diagram. Flap disagreement causes a level 2 alert, and the associated alert and procedure at the MFDU. The alternate flap procedure is given in the QRH. Operation of the alternate flap control deactivates the normal hydraulic flap system. It is not possible to restore the hydraulic mode while airborne. If the alternate flap control fails to operate the flaps, land with actual flap position. If necessary, use the landing procedure for flaps less than 25 degrees. In the event of a flap disagreement, normal flap speed limits apply and the flap position indication is available. Using the electrical alternate flap system, the flap travel time is considerably increased. Flap 25 is recommended for landing. The flap disagreement alert is inhibited as shown in the diagram. The speed brake lever sends an electrical signal to the hydraulic actuator, and the hydraulic actuator operates the speed brake surfaces. An electrical failure will cause the speed brake to retract if extended, but very slowly. If hydraulic failure is experienced, the speed brake will remain in the last selected position. The speed brake retracts due to aerodynamic forces when in is selected. In these circumstances, speed brake retraction is slower than normal. If a hydraulic failure occurs, the lift dampers are powered by the lift damper accumulator. This emergency power source is sufficient power for one extension and one retraction. If, after takeoff, the arming system does not automatically disarm, a level 1 alert is produced. An alert is presented at the MFDU. Disarm the lift dampers. The arming system has been manually disarmed. The alert for the lift damper system not being automatically disarmed is inhibited in every flight phase except climb, as shown in the diagram. A lift damper fault causes a level 1 alert, and an alert and associated procedure at the MFDU. Check the arming system is disarmed and do not arm it for landing. Manual extension of the lift dampers is available when reverse thrust is selected upon landing. Check the landing distance for the increased runway required for manual operation of the lift dumpers. The alerts for a system fault are inhibited as shown in the diagram. An unsafe lift dumper system generates a level 3 alert, and the relevant alert and procedure is presented at the MFDU. The local light for the lift dumpers is located at the lift dumper push button at the hydraulic panel. The lift dumper push button is guarded. Continue the procedure to cancel the alert. The alert has now been cancelled. Without lift dumpers, check the landing distance is sufficient for the extra runway length required. The alert for an unsafe lift dumper system is inhibited during the flight phases shown. A fault in the stick pusher system generates a level 2 alert, and the MFDUs state the associated alert and procedure. Complete the procedure to cancel the stick pusher fault alert. The stick pusher is now disconnected and automatic post-air stall recovery is not available. The stick pusher handle can only be reset on the ground. Finally, the FWS will inhibit the stick pusher fault alert as shown in the diagram.
The stall computer fault generates a level 1 alert and is given in the QRH. A stall computer fault is inhibited as shown in the diagram.
In this topic, we examined the secondary flight controls and their controls and indicators. We examined alternate operation of the flaps, arming of the lift dumper system, the stall prevention system, the takeoff configuration warnings and how the configuration can be tested prior to takeoff, and finally we discussed the alerts and procedures generated by related faults and saw how they are displayed at the MFDU.